Right, in this video I will do many examples on MLE. So the title of this video is Examples on MLE. I hope to do about 10 examples like I did previously. So we start with example 1. Suppose you have a random sample from an exponential distribution with parameter theta, and the question is to find the MLE of theta. So I'm going to follow because this is a continuous distribution, I'm going to follow the 4-step procedure that I gave you in the previous video. The first step, you may recall, is to find the likelihood function, which in this case is the product of the density function. The density function of this is theta times, okay. Now this is where your properties of product comes in. That's one of the videos I made as part of the preliminary section for this course. So if you take the product of this, you will get theta power n e minus theta times the sum of xi. Okay. So that's step 1. Step 2 is to take the log of the likelihood. So it's the log of L theta, which is the log of this, is going to be n log theta minus theta times the sum of xi. And step 3 is to take the derivative of this with respect to theta. So it's going to be n over theta minus the sum of xi. And setting this equal to 0, we need to solve for theta. So this implies that, let me call it theta hat, the solution of this equation. So theta hat is equal to n divided by the sum of xi, right, which is the same as saying 1 divided by x bar, the sample mean. Okay, so this is the solution of this equation. Now, to make sure that this is an MLE, we need to take the second order derivative. So that's the first order derivative of this. So it's going to be minus n over theta squared, which is clearly negative, right? So the conclusion is that the MLE for theta is 1 divided by the sample mean, right? So that completes example 1, which is a really easy one. Okay. Okay, let's go on to the next example. Example 2. So suppose x1 to xn or IID from a Poisson distribution with parameter theta. Question is once again, find the MLE of theta. Okay. So the first part is to write down the likelihood function. So in this case we are dealing with the discrete distribution, so we will follow the procedure for a discrete distribution. Right? So the likelihood is the product of the probability mass function for the Poisson distribution. So it's going to be this. So if you take the product of this using the rules for product, you will get this. So this is the likelihood function. The second step is to take the log of the likelihood So once again, I'm using when I take the log, I'm using the rules I gave you for product much early on in this course, right? So if you look at the videos under the preliminary section, you will see some of the rules. Right, so this is the log of the likelihood function. And step 3 is to take the derivative with respect to theta. Right, and set this to 0 and solve for theta. So once again, let me call the solution with the root theta hat. So theta hat would be 1 over m times the sum of xi, which is the sample mean. And step 4 is to check the second order derivative. The second order derivative is the derivative of this, which is minus which is clearly less than 0. So the conclusion is that so this completes example 2. Right. Next example is example 3. Suppose So you have a random sample from a normal distribution with mean equal to theta and variance equal to 1. Right? So find the MLE of theta. So this is a continuous distribution, so we will follow the procedure for the continuous data. So the first thing is to write down the likelihood, which is the product of the density function for the normal, which is this is the density function. This is the density function of the normal with mean theta and variance equal to 1. Right? Now if you take the product of this is what you will get. Step 2 is to take the log of the likelihood which is this. And step 3 is to take the derivative with respect to theta. Now, if you differentiate this, you need to use the chain rule. I'm sure you guys know what the chain rule is from your calculus. So first you differentiate the square. So it gives you 2 times xi minus theta. Then you differentiate what is inside the bracket. That gives you minus 1. Right, so this is what you get. So this is sum. The 2 and the 2 cancels, the minus and the minus cancel. So taking the sum inside, you get the sum of xi minus the sum of theta. So this is the sum of xi minus n theta. Right, and you set this to 0 and solve for theta. So you get theta hat, the root, equal to 1 over n times the sum of xi, which is the sample mean. Right. Now step 4 is to find the second order derivative of the log likelihood. So it's the first order derivative of this, which is minus n, which is negative. Right? So hence so this completes example 3. Next example is example 4. suppose IID with normal distribution, zero mean, and variance equal to theta square. Find the MLE of theta square. So the first step is to write down the likelihood. Again, this is a continuous distribution, so you follow the steps for the continuous case. Right, so this is the product of the density function for this distribution, which I'm sure you guys know. Okay. And taking the product of this, you get so this is the likelihood function. The next step is to take the log of the likelihood function . Well, the next step is to take the derivative . With respect to theta, you get so minus n over theta, and the derivative of this is 1 over theta cube . Now we set this to 0 and solve for theta squared, so that will give you 1 over n times the sum of xi squared. Okay, and the next step, step number 4, is to find the second order derivative, which is the first order derivative of this one. N over theta squared minus 3 over theta power 4 of the sum of xi squared. Right. Now we need to show that this is negative when theta hat squared is this. Right? There are several ways you can do this. One way, okay, I'll show you. One way is to do this. One, pull out the 1 over theta squared. Then in brackets you have n minus you have this, okay? In the next step, I'm gonna substitute wherever there is a theta. I'm gonna replace theta by theta hat in this step. So you get we get this brackets n minus okay. Alright, and in the next step I'm going to replace this guy here by what we got here, right? So right. Okay. Now you will see quite a few things. You see that this guy here goes out with this guy. Right. So you have what you have is simply 1 n minus 3 times n, right, which is equal to minus 2n divided by this, which is clearly negative. Okay, so what we have shown is that theta hat, the theta squared hat given by this is the MLE of theta squared. Alright, so this question is a little bit more involved than the previous questions, right? So that example 4, now example 5. Is the following, right? Suppose you have a variable x which has the binomial distribution with parameters m and theta, and the question is to find the MLE of theta, assuming n is known. Okay. Now this is a little bit tricky, because you will see here that you only have one x. You only have one data point, right? Right. So when you write down the first step, which is the likelihood function, you have to be a little careful, because remember, usually for a discrete distribution, the binomial is a discrete distribution. The likelihood is defined as the product I from 1 to n. N in this case is 1, because you only have one data, of p x. This is the definition I gave you earlier, but the difference here is that you have n equal to 1. All right, so you have I from 1 to 1 of this, which is simply the PMF of the binomial distribution, right, which is equal to m choose x theta over x 1 minus theta m minus x. So whenever you have only one data, the likelihood is the same as the PMF in this case, because it's a discrete data. But if it were continuous data, the likelihood would be the same as the density function whenever you have just a single data point. Okay. All right. So that's the part you have to be careful about. The second part is to take the log of the likelihood, which is the log of this. And the third part, part 3, is to take the derivative so derivative of this with respect to theta, it is x by theta minus m minus x by 1 minus theta, and we set this to 0 and solve for theta. So let's see what happens. So this is the same as x by theta equal to m minus x by 1 minus theta. This is the same as x times this equal to this. And solving this for theta, you get theta hat equal to x by m. And the step number 4 is to take the second order derivative. So it's the first order derivative of this one. So it's going to be minus x over theta squared minus m minus x over 1 minus theta squared. And this is clearly less than 0, right? So hence alright, so this completes example 5. Next, example 6. Suppose this is kind of related to the previous example. Suppose you have a random sample x1 to xn, which are IID from a binomial distribution with parameters m and theta, and find the MLE of theta, assuming that m is known. So as I said, in the previous example, you may recall that we only had one data on this, but here we have n data points coming from the same distribution, right? So that's the key difference, and you will see what difference it makes to the answer. So the first step is to write down the likelihood, which is, in this case, because you have n data points, it will be the product I from 1 to n of the probability mass function of this, which is okay. So if you take the product of this, this is what you will get. theta power sum of xi, and 1 minus theta power the sum of n minus xi. Okay. Alright, so this is equal to theta power sum of xi. Now this guy here, the sum of m minus xi, can be written, if you take the sum inside the brackets, you can write it like follows. The sum of m is going to give you m times n, and then the sum of xi. Okay, so this is what you get. And step number 2 is to take the log of the likelihood. So it's the log of this. That will give you the following. Right, plus the log of this term will be and the log of this term is right, so this is the log of the likelihood function. And the next step is to take the derivative of this with respect to theta. So if you differentiate this with respect to theta, you get this, right? And you set this to 0 and solve for theta. So this will be equal to theta times here, and solving this equation for theta will give you theta hat equal to, if I call this as the solution, equal to 1 divided by mn times the sum of xi. Right, now the final step is to show that the second derivative is negative. So the second derivative is the derivative of this one with respect to theta. So it's going to be minus this is clearly negative, right? So hence is the MLE of theta. Alright, so this, so you see the difference between this example, example 6, and the previous example, which is example 5. So the difference is that here we have n data points from binomial distribution with these parameters, and in the previous example we had just one. So that made a difference to all the calculations we made here. Okay. The next example is example 7. This involves involves more calculations compared to the previous ones. Alright, so let me show you how to do this. Suppose you have data x1 to xn IID from a normal distribution with mean equal to theta and the variance equal to theta squared. And the question is to find the MLE of theta. Okay. So the first step, as always, is to write down the likelihood function, which is the product of the density function of this, which is this, right? Okay. Now you should take the product of this, and you will get the following. Okay, and step 2 is to take the log of this. So it becomes minus n over 2 minus n log theta minus 2 theta squared times the sum of xi minus theta squared. Right? Now what I'm going to do is I'm going to open the brackets here. Remember, when you open the brackets you get 3 terms: a squared plus 2ab plus b squared. Right? So the first term is xi squared, the second term is 2 xi theta, the third term is theta squared. So after opening the brackets you get these 3 terms. Right. In the next step I'm going to take the sum inside the brackets, right? So you get 3 different sums. And for the second term you get minus 2 theta goes with this one, so you get plus 1 over theta times the sum of xi. For the third term, theta squared and theta squared cancel, so you get minus n over 2. So this is the simplified form of the log likelihood function, right? Okay, now step 3, we're gonna take the derivative of this with respect to theta. So let's do that. So it's minus n over theta, the derivative of this. The derivative of this is 1 over theta cube right? And the derivative of this is minus 1 over theta squared times the sum of xi. Okay, and we're going to set this to 0 and solve for theta. Okay. Now, what I'm going to do next is I'm going to multiply this whole thing here by theta cube, right? And you should do that. This is what you will get. You get n theta squared plus the sum of xi squared minus theta times the sum of xi, okay, equal to 0. And in the next step I'm gonna multiply the whole thing by a negative number, so you get n theta squared minus this plus theta and this is equal to 0. Now for later use, let me call this equation star. Now to solve it, what we need to do is to solve this equation for theta. Now you see immediately here what you have is a quadratic equation on theta. You may recall the following formula, that you should have a theta squared plus b theta plus c equal to 0. Then the solution for theta is minus b plus or minus square root of b squared minus 4ac divided by 2a. Alright, so this is the, I'm sure all of you know this from many years ago, right? This is the solution for a quadratic equation, right? And I'm gonna use this to solve star, okay? Alright guys, here we are. So using this equation, we can solve equation star to get the following. So this implies that theta hat is equal to minus b. Minus b is the sum of xi, right, plus or minus square root b squared. Your b squared is this minus 4ac, which is going to be 4 times n plus 4n times the sum of xi squared divided by 2a, which is 2n. Alright, now the question is, you see you have two roots here. One is plus, one is minus. Which one is the correct one, or which one is the valid one? That's the question we must answer right now. Alright, so to answer that question, remember that theta squared denotes the variance of the normal distribution, and theta denotes the standard deviation. Alright, theta. Alright, so hence, by definition, variance and standard deviations are positive parameters, right? Right. So of these two roots, the one with the negative cannot be valid because you have minus sum of xi minus, which is clearly a negative root, right? And the theta cannot be negative because theta represents standard deviation, right? So what I'm saying is that of the two roots that we have, the valid root is the one with the plus. In other words, minus sum of xi plus this divided by 2n. Alright, so the valid root for theta hat is the one is the following, is the minus of the sum of xi plus plus 4n divided by 2n. So this is the valid root, right? Now we are not done yet because we still have to show step 4. Step 4 is to show that the second order derivative is negative. So let's see how we can do that. Okay. Okay, step 4. So this is going to be the first order derivative of the first derivative, right? So it's going to be the following. Now, what I'm going to do in the next step is to take the common factor 1 over theta power 4, and in brackets we will have n theta squared minus 3 times sum of xi squared plus 2 theta times sum of xi. Now we need to show that this gap is negative, right? Right. In order to do that, let me call this equation triple star. Now, if you go back to the thing that we did earlier, you see this equation here, star, which I call a star. From star, from equation star, you can see that the following is true. That is, theta times sum of xi is equal to minus of n theta squared plus the sum of xi squared, right? Which implies that 2 theta times sum of xi is equal to minus 2n theta squared plus 2 times sum of xi squared. Okay. Now I'm going to call this equation double star. All right, and also let me put this thing in a box. Okay. All right. Now what I'm going to do is I'm going to substitute. You see, there is a term here called 2 theta times sum of xi. So in place of this, I'm going to substitute this. Right? So if you do that, this is what you will get. So substitute star, sorry, double star into triple star. So what I'm doing is basically replacing this term here by this, right? And if you do that, this is what you will get. Okay, this you get 1 divided by theta 4. Yeah, and n squared minus 2n theta, sorry, n theta squared minus 2n theta squared will give you minus n theta squared, and minus 3 sum of xi squared plus 2 sum of xi squared will give you minus of this, right? And clearly this is a negative number, right? So clearly, because you have minus here and you have minus here, and xi squared cannot be negative, it must be non-negative, right? So this whole thing is negative. So hence we have shown that the second order derivative is negative. So the conclusion is that hence theta hat equal to hence this, right, is the MLE of theta, right? So this, I know this question is a little bit involved, but the calculations are not something you haven't learned, right? I mean, basically I'm using the quadratic equation and the roots of a quadratic equation. I'm sure you are familiar with that stuff. Okay. So let's go to the next question. So this is example 7, and the next example is example 8. Here, suppose so you have a random sample from this density where x is greater than 1, and the question is to find the MLE of A, right? So here's the first step is to write down the likelihood function of A, which is this. Now I should take the product of this using the rules I mentioned to give you earlier. This is what you will get. Okay. So this is step 1. Step 2 is to take the log of the likelihood function. Right. Step 3 is to take the derivative. And set this to 0 and solve for A. So you get A hat equal to this. And finally, step 4. The second order derivative, which is the first order derivative of this, which is minus n over a squared, which is clearly less than 0. Right? So the conclusion is that is the MLE of A. Okay, so that completes example 8. Now, next example is example 9. Right, so suppose We have a random sample from an exponential distribution with parameter theta, and find the MLE of the probability that x is less than 1. Alright? Now, to do a question like this, the first thing you must do is to find an expression for this. Now, this is simply the integral from 0 to 1 of the density of this, which is theta okay. So this is going to be theta times the integral of this, which is you take the limits from 0 to 1, and this is theta times the limit at 1 is going to be here minus theta. The limit at 0 is 1 divided by minus theta. So this is going to be 1 minus e of minus theta. Alright. Now this, because theta is a positive number, right? Positive is, so this is a one-to-one function of theta. Okay, it's a one-to-one function of theta. So we can use one of the properties that I mentioned earlier in the previous video, that if you have a one-to-one function of theta, and you know the MLE for theta, then you know the MLE for the one-to-one function. And that property is known as the invariance property or invariance principle. Right? Now, by example 1, the first example we did in this video, by example 1, the MLE of theta is 1 over x bar. Right? Alright, now by the invariance property, which I mentioned in the last video, the MLE of the probability that x is less than 1, which I'm going to denote like this, a big hat, is going to be 1 minus e. I'm going to replace theta by theta hat. So this is 1 minus e minus 1 over x bar. So I hope you understand. So this is the power of the invariance principle. That is, if you have a one-to-one function of theta, which is the case, this is a one-to-one function of theta, right? And you know the MLE for theta, then you know the MLE for this, which is this, right? Alright, so that's example 9. The final example I'm going to do in this video is example 10. So here, suppose right. So the first thing, once again here, the first thing you must do is to find an expression for this, which is the probability that x is less than 0. So the probability that x is less than 0, x is a normal variable with mean theta and variance 1. So the first thing I'm going to do is I'm going to standardize x by subtracting the mean and dividing by the standard deviation. Okay. Now this is the standard normal variable, so this is the probability that m01 is less than minus theta. And you may recall from earlier that the CDF of a standard normal variable is denoted by capital Phi. And once again, this as a function of theta, this as a function of theta is a 1-to-1 function of theta. Alright, now one of the early examples I did in this video, I think it was, correct me if I'm wrong, by example 3 in this video, we know the MLE for theta to be equal to the sample mean x bar, right? Okay, hence by the invariance property, the MLE for the probability that x is less than 0, which I'm going to denote by this, is equal to phi at minus theta hat, which is phi at minus x bar. So this is another example on the use of the invariance property. Right? So this completes example 10 and also completes the video on examples on MLE. If you like me to do more examples, please let me know. In the next video, I will talk about some preliminaries that we need to talk about confidence intervals. Because so far we only talked about point estimators. So MLE is a point estimator. That is, given a parameter theta, it gives you an estimator for theta. But how do you construct an interval of estimators for a given parameter? So that is going to be the next topic. But before I can talk about it, I need to talk about some preliminaries, right? And that will be the next video.